Hi everyone, welcome to Dr. RCM Academy. In this session, I will be discussing what is current density and what is the relation between them, and then we will be deriving a small equation for continuity of current. So as we know, what is a current? So it is the electric charges in motion which constitutes a current. In other words, I'll define it is the rate of flow of charge at a specified point. It is the rate of flow of charge at a specified point or across a specified surface. We call it as electric current. And mathematically, I can represent this definition as current, which is equals to rate of flow of charge with respect to time. So that is dq by dt. So this is the electric current, and we represent electric current in terms of amperes. So after defining what is electric current, let us define what is electric current density. So it is nothing but, if I consider a conductor, current carrying conductor, so there is a rate of change of charges. That is nothing but the current. The current is flowing through a conductor. I will just take a cross section of the conductor. The current that is crossing this surface, I call it as a current density. So I define current density is the current passing through unit surface area. This is the surface area I am considering. How much current is passed through this surface area? So I call it as a current density. So for which I will consider a small differential surface ds. So in this differential surface ds, let the current flowing through is di. So differential current passing through differential surface. So according to surface current density, it is current per area. So that is di by ds. I have taken a small differential surface. So in this differential surface, the current is di. Therefore, current per differential surface. So I call it as the current density. So I will just rewrite this expression as di is equals to, I will cross multiply this, that is vector j dot vector ds. This is the differential current passing through this small differential surface. This is the differential current passing through differential surface. So if I want the total current, so I can integrate throughout the entire surface, that is S. Before that, so this di can be written as, this is vector j, the bold letter indicates it is vector j, which can be represented as magnitude into unit vector. Similarly, vector ds can be represented as magnitude into unit vector, and these are normal to the surface. Both the current density and the differential surface, they are normal to the surface. Therefore, an dot an is equals to 1. Therefore, di is equals to j dot ds. So if I integrate this throughout the surface S, then I get the total current, which is I, which is equals to surface integral, the entire surface I am considering, that is the total surface integral of j dot ds. So this is the total current passing through the entire surface. This is the current density, and the relation between current density, which I denote it as j, and the current is I. The relation between I and j is I is equals to surface integral of j dot ds. We have defined what is current, we have defined what is current density. With the help of this relation, let us define one important equation called continuity equation. So what is this continuity equation is? So it is based on the principle of conservation of charge. So what is principle of conservation of charge is, charges can neither be created nor be destroyed. So it cannot be created or it cannot be destroyed. So we just now defined the relation between I and J, that is current and current density. I is equals to surface integral of J dot ds. Now let us take one closed surface, and if the current is flowing outside the closed surface, then which means that there is a flow of positive charges from the surface. Hence, I write it as outflow of positive charges, means decrease in the charge inside the closed surface. When the current is moving out from the closed surface, meaning that the charges are decreasing. Charges are decreasing because the current is flowing out. So that can be mathematically denoted as minus dqi by dt, where qi is the charge and the rate of flow of charge, I write it as dq by dt, and this negative sign indicates that is the rate of decrease of charge inside the closed surface. So when the current is flowing out, the charges are decreasing, so that decrease I represent it as minus. So it is minus rate of change of the charge with respect to time. So therefore, I rewrite this above equation. I is equals to surface integral of J dot ds. I is current is flowing out, therefore it is minus dqi by dt. So let me represent this as an integral form. This is also called integral form of continuity equation. So again the meaning is, continuity equation is, the charges can neither be created nor be destroyed. So the charges are moving out, that is nothing but the current. So let us represent this equation in differential form or point form, we call it as. So for which we remember the divergence theorem. So what is divergence theorem? We know that it is closed loop surface integral of J dot ds is equals to volume integral of del dot J into dV. This is called divergence theorem, Gauss divergence theorem, which I have explained in the previous videos. Now from the previous equation, what is this? Surface integral of J dot ds, that is nothing but the current, outflow of the current, which I represented as minus dq by dt, which is equals to volume integral of divergence of that electric flux density, so in a given volume. So therefore, I represent now Q in terms of volume charge density, and we know from the definition of volume charge density, total charge by volume, rho v equals to Q by dV. In other words, Q equals to volume integral of rho v into dV. This is called volume integral. So rho v into dV. So in place of Qi, I will substitute it as volume integral of rho v into dV. The above equation now it becomes, so it is volume integral of del dot J dV can be written as, so it is minus d by dt. In place of Qi, I am writing volume integral of rho v into dV from this equation. So which is nothing but, if I send this differentiation inside, so it becomes partial derivatives. So it is, sorry, there is a 2 minus here, so actually there is only 1 minus. So dou rho v by dou t into dV. Now, so I equate this, volume integral of del dot J dV equals to minus, there is only 1 minus actually, so wrongly written 2 minuses here, volume integral of dou rho v by dou t into dV. So this is applicable for the entire or any kind of volume. So even it for the small differential volume. Therefore, so I can write, so del dot J del V equals to minus dou rho v by dou t into del V. So on both the sides you have a differential volume. So therefore they get cancels. We get del dot j equals to minus dou rho v by dou t. If you look into this equation, del dot j is nothing but divergence of current density, which is equals to minus dou rho v by dou t. So the rate of change of charge density in a given volume is equals to divergence, and the negative again indicates the charges are flowing out, it is emptying, so it is flowing out. So this is called the differential form or the point form of the continuity equation of current. This is a very important equation. So which states that the current diverging from a small volume, current diverging from a small volume per unit volume is equal to rate of decrease, this negative sign indicates it is decrease, rate of decrease of charge per unit volume at every point. This holds good. At every point this equation holds good. This is the continuity equation, which again states that charges can neither be created nor be destroyed. The amount of divergence is equals to rate of change in the charges, that is decrease in the charges. Thank you for watching the video. Still, those who have not subscribed my channel, kindly subscribe. Also, you can like and share to your friends. So any relevant videos required, post it in the comment box. Thank you.